Measurements that we take through acoustic analysis give us a different set of insights into productions than we would achieve through the impressionistic analysis techniques that we normally start with as we begin doing phonetic and phonological analysis. But ultimately, our research goals across techniques are the same. We're trying to describe the sounds of language varieties, to characterize the sound systems of those varieties and the rules underlying their sound systems, and to understand the phonetic and phonological components of the human capacity for language. As such, while we have to think about acoustic data differently from impressionistic data, fundamentally, the analytic approaches we take to move from phonetic data to phonological analysis are the same across techniques. For instance, this is a plot of vowel space for a woman I interviewed in Kansas City in the United States. It shows normalized single-point measurements of F1 and F2 of the vowel ah. Each word on the plot shows the word that she spoke during her interview, which contains a vowel that American English speakers would traditionally be expected to produce as an ah with primary stress. The triangles are centered on each vowel token's F1 and F2 measurement. Even though we expect these words to all contain the same vowel, there's obviously two clusters of productions. The tokens that are plotted with an unfilled triangle cluster in a low central area of vowel space, around an F1 of about 900 Hz and an F2 of about 1600 Hz. If you were just listening to these tokens and impressionistically transcribing them in IPA, you would probably transcribe these as the IPA character for a low central vowel or a low front vowel. For simplicity, we'll use ah. By contrast, the tokens that are plotted with filled triangle occur higher and fronter in vowel space. They're spread out over a pretty big range in F2, but we might center that cluster around maybe 600 Hz in F1 and 2400 Hz in F2. If you were listening to these tokens and impressionistically coding, you'd likely transcribe them with something like the mid-front lax vowel. So if you were doing impressionistic analysis of the way that this speaker realizes her low front vowel phoneme, you'd end up with two surface-level allophones, ah and eh. You would then go through the steps of phonological analysis. Step 1, you would look for minimal pairs. There are no minimal pairs where words differ just on the basis of a contrast between ah and eh, so you would go to step 2. You would make a column for ah and another column for eh, and then you'd list the phonetic environments that each allophone occurs in. In step 3, you'd compare the phonetic environments that each allophone occurs in and find that they don't occur in the same environment. The allophones realized before eh always occur before a nasal consonant, while the allophones before ah never occur before a nasal consonant. The allophones are therefore in complementary distribution, so they must be allophones of the same underlying phoneme. In step 4, you'd propose rules. Here it makes sense for the allophone ah to correspond to the underlying phoneme, since it occurs in the majority of environments and we can't make predictions about where it will occur. On the other hand, we know that this speaker will always have the allophone eh before nasal consonants. So we would propose that in this speaker's variety of American English, the low front vowel is produced as the mid-front vowel when it occurs in the environment of a following nasal consonant. Then, of course, we'd test our rules against the data and find that they explain every production we observe. We'd look for phonetic explanations and find that following nasal consonants often result in vowels being fronted or raised in Englishes and cross-linguistically. And if necessary, we'd further refine our rules. So we're actually following the same analytic approaches with acoustic data that we have already mastered for impressionistic data. In practice, probably the biggest difference is that acoustic data are much messier than the idealized transcriptions analysts create during impressionistic coding. This is a reality of speech. Speakers don't produce utterances of a vowel or any other phonetic unit identically across productions. Even if the speaker says the same sound over and over and over again under identical conditions in the same setting, the literal acoustic values of those productions will be different. So single point F1 and F2 measurements of utterances of a vowel will occur in a cloud of vowel space rather than at some perfect unified single point. As such, we usually need to extrapolate away from the very small details of individual productions to a broader characterization of the data. With vowels, we often calculate a mean value for the entire class of allophones. That's what I was doing very crudely when I said there are Kansas Cityans prenasal allophones of A clustered around 600 Hz in F1 and 2400 Hz in F2. We also often talk about differences among allophones in more general spatial terms rather than trying to reduce them to IPA symbols. For instance, in my research, I would tend to talk about our Kansas Cityans prenasal allophones as being raised and fronted relative to allophones in other environments. I would be drawing on the phonological concepts of vowel height and frontness as depicted in the IPA vowel chart. So my actual phonological analysis of this acoustic phonetic data set would be that in Kansas City, the vowel A raises and fronts when it occurs before a nasal consonant. And I reach that by drawing on the same phonological analysis techniques that we learned to analyze impressionistic data.